All right, so to continue our discussions with machine design, I'll just repeat about functions, design requirements, and evaluation. So functions are just adjectives that describes what the device must do. Okay, so using, this is the key term here, general non-quantitative statements. So it's just a basic description of what the device must do. The design requirements are more detailed. So in relation to functions, this where functions is non-quantitative, design requirements are quantitative statements of expected performance levels, environmental conditions in which the device must operate, limitation space, weight, or availability of materials or type of materials. And then evaluation criteria are statements of desirable qualitative characteristics of a design that assist the designer in deciding which alternative design is optimum. This is the technical feasibility of different alternatives that you will be selecting on. So example, design of a speed reducer for a power transmission system for a tractor. So example of functions. So as we have seen that functions are non-quantitative statements that just describes what the device must do. So to receive power from the tractor's engine. So it's a very general statement to transmit the power through machine elements that reduce the rotational speed to a desired value, and to deliver the power at lower speed to an output shaft that ultimately drives the wheels of the tractor. Now let's look at example design requirements. The reducer must transmit 15 horsepower. So here we have a quantitative limitation for power. Okay. Then input is from two-cylinder. Again, there's this two-cylinder gasoline engine with rotational speed of 2000 RPM. So now you have an input rotational. So you have rotational speed input. And then number 3, output delivers power to rotational speed in the range of 290 to 295. So you have the rotational speed output. Now, this relationship between input and output, so you could create kind of a transfer function using gears where you have your input speed and your output speed. Transfer function for gears. So now you have a gear system. So those are really very specific, detailed values that will help you out in your design. Number 4, mechanical efficiency is greater than 95%. Minimum output torque capacity of the reducer should be 3,050 pound-inch. Again, those are very detailed values. Reducer output is connected to the drive shaft for the wheels of a farm tractor. The input and output shaft must be inline. Reducer is to be fastened to a rigid steel frame of the tractor. Small size is desirable, so you have a 20-inch by 20-inch area and a maximum height of 24-inch. The tractor is expected to operate 8 hours per day, 5 days per week, with a design life of 10 years. As I have mentioned the other week, that this is an important factor, especially for machine elements that are dynamic or moving. The reducer must be protected from the weather and must be capable of operating anywhere in the United States at temperature ranging from 0 to 130 degrees Fahrenheit. Flexible couplings will be used on the input and output shaft to prohibit axial and bending loads. So again here, the type of loading. Production quantity is 10,000 units per year. Moderate cost is critical to successful marketing. All government and industry safety standards must be met. Now, this is really a very good example, especially that you will be going to your senior year next year and you will be developing these types of functions and design requirements for your senior design projects. And then these are evaluation criteria: safety, performance, ease of manufacture, ease of service, ease of operation, low initial cost, low operating and maintenance cost, small size and low weight, low noise, use of readily available materials, prudent use of both uniquely designed parts and commercially available components, and appearance that is attractive and appropriate to the application. So these are evaluation criteria. Now, there are some engineering evaluation methods where the criteria are ranked or are weighted. So here it is just not weighted, they just provided this certain criteria. Now it's up to the designer which of these criteria are the most important one when it comes to the selection of the different alternatives. So machine design for me is a kind of a misnomer, because actually we're not designing a machine, but here in machine design, what we are doing is we are designing machine elements which are integrated. So it's the integration of machine elements into a mechanical design. So mechanical design is the process of designing and or selecting mechanical components. So there are components, as an example, roller bearings, which are already made, different sizes, different types. Now all we have to do is to do the calculation of the loading, the time, the service life, and other factors which will help us select the optimum component to use for a certain application. And then putting them together to accomplish a desired function. Okay? So that is the integration of machine elements. And then the process of designing, selecting mechanical components, then integrating them together or putting them together to accomplish a desired function. So an example of that is the speed reducer. So if we see here the speed reducer, we could start by looking at, from control systems, we have our transfer function block diagram, and we have the input and output. And so from this block diagram, we could see the physical implementation of the speed reducer transfer function. Okay, now this one has a certain number of machine components that we could see. So let's look at the different machine components that makes up the speed reducer. So we have number one, you have shaft. Okay, so in chapter 12 we will learn how to design shafts. So if you observe here, there are 3 shafts, right? 1, 2, 3, and you could observe with the shaft that they don't have a uniform diameter along its length. Okay, that is because of the different loading that the shaft is subjected to at the different points. So at the different points, then we will calculate the diameters of the shaft at those different points, thereby producing this shaft that has different diameters along its length. Okay, so there's a shaft, there is this bearings. So we will also look at bearings in chapter, I think it's chapter 14. And then number 3, these here are gears. Gears are chapters 8, 9, and 10. And then number 4, so you could see here the key. So we will also look at how to design keys and splines. And you have the housing. You have the seal. And what else do we have here? I think that's most of the parts that make up the speed reducer. Okay, and so each of those, for example, the shaft needs, we could not select shaft. We have to design the whole shaft, the diameter along its length. Bearings we can select. Gears, either you could manufacture your own, or you could buy pre-made gears. Keys, again, you could also buy or you could manufacture. Housing is manufactured. Seals are selected. Okay, so those are an example of a machine design project, a speed reducer. And this will also be, you will be creating or doing as a final project for this class, a power transmission, design a power transmission system for a certain application. So I hope that that makes sense. If we go back to this example here, we could see that this is an assembly of different machine elements. So once we have, identified a certain machine element, for example, that we are looking at this shaft here, okay? So as we look at the shaft there, we go back here, there's another bearing there. From the another machine or engine or motor that will drive your speed reducer. Okay, so, and then this is the design calculation, which could be applied to most of engineering problems. So, but this one is basically for machine design. Identify the machine element to be designed. Okay, so we go here, identify a machine element being designed, draw a sketch of the element, show in the sketch the forces acting on it. So let's take, we can draw kind of the shaft there, and so we will have the reaction, draw the sketch of forces acting. So this is force for bearing 1, there is force for bearing 2, and then there is force from the gears. Okay, and then there is an input moment here. Now that you have shown the forces acting of the element, identify the kind of analysis to be performed. So from strength of materials class, we could see that this one is subjected to bending stress and torsional stress. Okay, so along the axis of the shaft, we could see that there is no force acting there, so there is no axial stress on the shaft. And then once we have identified the kind of stress, we will do then the stress analysis based on the loading, again, the bending stress and the torsional stress. Then list all given data and assumptions, write all the formulas to be used, and then solve the problem. Insert the data, check the units, perform the computations, and then you evaluate your results. Now, this is a very good guidelines when doing a calculation, not only for machine design, but for any design aspect in engineering, especially when you go into practice. So just, read this method and also try to, if you could memorize it. And this will be really helpful, especially as I have mentioned before, when you go for interviews and you are asked like, hey, can you describe a design method? And you could easily speak out or describe this design calculation that we have here. The design, identify the machine element to be identify the machine element that to be designed. We then draw the sketch of the element and show in the sketch the forces acting on. All right, so here is an example of a design of a bar to support a gear. Okay, so we have a gear here that is being supported by the bar and it is being suspended, and we have a 2,050 pound gear. So the goal here is to design a bar. It could be a round bar, it could be a square bar, or it could be an I-beam. Okay? So when we look at this example, what I want to show here, okay, so let's go back. So it will be the supporting bar, okay? So machine element is the supporting bar. And then the bar is to hold, okay? We are given that the length of the bar is 60 inches and the load is 50 pounds. And then supporting hangers, okay, supporting hangers are 24 inches apart. Okay, so we could see this one here. The supporting hangers 24 inches apart. Okay, so once we have idea element, okay, so if we draw here, we call it the FBD or the free body diagram, or you could also say Professor Bolanon-Duke. Okay, so you have the weight, okay, of the bar, and then you have the force. I'm sorry, the weight of the bar is, that's a wrong free body diagram. So we'll draw the bar again. So the weight is distributed here, okay? Weight of the bar. And then that's the reaction at this point here. Okay. So if we draw the bar again with the forces, we have so 20, 50, 10, 25. You also have 10, 25. Obviously, this is also 10. This is a very straightforward problem. So by looking at the free body diagram, we could see that the bar is under bending stress. Okay, so here in machine design, I want you to have this very procedural and systematic way of approaching a problem. And I want to see this in a homework as shown like this, and also during the exam, so I could easily follow your thought process as you solve the problem. So bending stress is MC over I, right? Where I is your moment of inertia and C is at the center of the bar, or it could also be expressed as M over S, where S is equal to I over C. So now since the bar is under bending stress, we have to calculate the moment from the free body diagram. And so in order to calculate the moment from the free body diagram, so we have the loading diagram here, the shear diagram. And so from the load, from the free body diagram, we could draw the shear, okay? So going up, no force, and then there's force going down, and then there's no force going down, no force, and then going up. So the shear diagram should close, and that is also similar with the moment diagram. And so from your shear, so this is positive shear there, meaning you have a positive moment, no shear, 0, and then negative moment. So that is your, so this is your load. This is the shear diagram. And this is the moment diagram. So this means that there's a lot of things that we need to, or not we, but you need to review in your statics class, especially this shear moment diagram. So if you have forgotten this, try to brush up on how to create a shear moment diagram. And so from there, once we have calculated the moment, so the maximum moment here based on the shear is, so this is 1025, and that distance there is 18 inch, right? Because that's 18, 24, 18, it will give us 60. So the maximum moment is 1025 times 18. That will give us 18,450. Okay. Pound inch. So now we have calculated our moment. Now we have, okay, so we M over S. So this is equal to 18,450 over S. Okay. Now, here in machine design, okay, this is a very good illustration here. There's a number of things that we can do. Okay. So the first one is we can select the geometry back. Okay. We can select the geometry of the design. So select geometry. So in this case, what we wanted is, for example, if we have the bar here, that's the length of the bar, we could select a rectangular cross-sectional area, or you could select an I-beam. Okay? Or you could select a round bar. So that's what I mean by geometry. So you could select, because we already know the length, but we don't know what's the geometry. Okay, so the geometry now is a function of the section modulus S. Or the other thing is you could select the type of material. Okay, so once you select, so for the different type of materials you have, you will be provided with the yield strength, the properties of the material, and the ultimate strength, which then you could use for your allowable bending stress. Okay, so here let's just say that, okay, we want to assume a rectangular section. Okay, so if we assume a rectangular section, then our section modulus will be equal to TH squared over 6. So we could see that in the table later, where that is the thickness and that is the height of. Okay, and then from there we could then set that we could let h, the height, be equal to 3t, and so simplifies our section modulus to S to be equal to t 3t squared over 6. And then the next part is we assume a material. So let's say we will use SAE 1040. So for SAE 1040, the yield strength is equal to 42,000 psi. Okay, pounds per square inch. So for the bending stress, we then set that the allowable bending stress is equal to the yield strength divided by the factor of safety. So let's just say that this factor of safety is 2. So 42,000 over 2 will give us 21,000 psi as our design stress. Right? So using that design stress, so we know that the stress is bending stress is moment divided by the section modulus. We already have our design stress, 21,000 psi. That is the allowable stress that we want for our bar. And the maximum moment, as we have calculated here, is 18,450 pound inch. And then our section modulus is 9 t cube over 6. So from there, we could calculate the thickness. And since thickness is equal, once we have calculated thickness, we could calculate the height, which is 3 times the thickness. Okay. And so now we have designed the material with a specific thickness and with a specific height and a length of 60 inch. So that completes the design process for the bar supporting the gear. Okay. So the thickness that we have calculated from here will give us 0.837 inch. Okay. Now the preferred basic sizes are standard sizes that may be available in hardware or a supplier, in catalogs. And so once we have calculated a value, we then go. Oh man, what happened there? You see, for example. And then I also want to talk about these preferred basic sizes. Okay, so the preferred basic sizes, this is a very useful table here, because let's take to the preferred basic size, that's 0.837. So we will look at the fractional number in inches. Okay, 0.837. So there is no 0.837 here. But once we will be able to get that value, we will just then select the one that is closest to 0.837. And once we have selected that one, then we will use that. So use this appendix 2, the preferred basic sizes, to not to simplify, but to choose the final dimensioning of your machine elements that you will calculate. Okay? So so your answers must be within these values in appendix 2. And these are just, we will look at the different appendices. This is just an example of American screw threads, type of threading, coarse threads, fine threads, and then other as you receive your textbook, try to look at the appendix part, and you could see there section properties, moment of inertia in the different axes, XX, YY, ZZ. We will discuss that more as we look into the applications of these tables. And then typical units is machine design. You have length, area, force, mass, time. You have the US customary unit and the SI unit. Okay, so try to familiarize yourself with these different units and different factors that these units are designated for. Okay. Then you have conversion factors here. Like what I have told the seniors as we are trying to review for their FE, sometimes it is, not sometimes, but it is really very helpful if you memorize these conversion factors, especially the very common ones, because as you take those types of exams, then you won't spend any time looking at conversion factors tables because you already have that at the back of your mind. Okay, so that stops my lecture for this chapter, and then I'll see you on Friday and we will continue with chapter 2. Okay, thank you very much.